So let's talk about the electric field produced by a charged rod. So I've already drawn a charged rod. So it's positively charged and it has length L. And I've drawn a dot where I think we can come up with an equation to describe the electric field. Now, describing the electric field around an extended charged object can be a little bit more complicated than a point source, but all the same principles apply. The way we're going to look at this is to consider what contribution a small component of that larger object makes to the field, and then we're going to add up all the different little components along the length of this rod. Okay, so let's take a look a little closer. Okay, and we'll pick a different color. So let's say that we want to look at the impact of this area here. So we could say that this is some sort of dq. So we've got a section of this extended object and it's going to have a certain amount of charge. It's going to be a relatively small amount of charge. I'm drawing this a little bigger than we may consider it to be, just to make it a little easier to see. And so we've got some dq here, and that dq is going to be some distance away from our point where we're going to consider what the field is. Okay, so let's consider the distance from this dq to our point. There we go. All right, so what is this distance? Well, we can work that out with a little bit of trigonometry if we want. We can have some sort of distance r here for the distance from the point to the closest location along the rod. And then we can also define y as being the distance from that point in the middle of the rod to our dq. And from that, we're going to know that the distance between our dq and our point is going to be given by, and we could say, well, we could draw it as well, d is a bit confusing because we use it in calculus. But we have some sort of distance that's going to be the square root of y squared plus r squared. And that gives us the distance between this point of interest and our dq. Now, the other thing that we're going to need to think about is the charge density. And so there's going to be some sort of total charge Q on this object. And if we divide that by L, then we're able to get this idea for a charge density, a linear charge density, which we will represent with lambda. And that density enables us to figure out, well, how much charge is in any little dq that we might define. Of course, we'll need to have some sort of dy or dl that is the length associated with that as well. Okay, so what about the electric field that is created at the point due to dq? Okay, well, let's zoom out just a little bit, give ourselves a bit of room here, and we can draw this, and we'll keep it consistent with our dq notation. So we're going to have a electric field that is basically like this, where we've got I can get a little better of an arrow here. So we're going to have this electric field produced by dq. And so what we can also do is break that into components. That's going to be pretty important pretty soon. And so we could think about it as having a component in the x direction. So we could then break it into having a component as well in the y direction. It's not perfect, but it's pretty close. Okay. So we'll draw this and notate it as dEx and dEy. So that would be the x and the y component of the electric field at that point produced by dq. All right. So there's also an angle that we have not noted here yet, and that is right here. Okay, so there's some angle there. And that's going to be important because we're going to be interested in all the dq's along the full length of L. But this example will lead us into that. Okay, so what if we want to then set out an equation that describes what we have for an electric field? Let's back out here a little bit and let's write out our equation. So we can follow the way that we've seen an electric field equation before, but in this case, instead of just saying, normally it would be the electric field is going to be equal to K, right, our Coulomb constant, Q, our charge, and then it'll be over some sort of distance. So we could say, well, this would normally be our distance squared. In this case, it's going to be a little different because we're not actually calculating yet the total electric field. What we're calculating is the dE caused by our dQ. Okay, so we've got a small piece of the electric charge that's producing a small piece of the electric field at that point. In addition, instead of R in our equation, what we're going to have is this distance, square root of y squared plus r squared in the diagram, and that's all squared. And so because that's all squared, this will end up being K dQ over y squared plus r squared. Okay. So the other thing that we want to consider is, well, what would be the electric field in the x direction? Because let's take a look at what's going to happen when we integrate along L to capture the contribution of every little piece. So later on, what we're going to do is we're also going to have, because this point here is going to be, it's chosen for a good reason. It's right along the middle. So what we're going to do is consider that we also have a point here where this dQ is also going to have a contribution, and that contribution is going to be right like this, and then it will also be broken down into x and y components. And what you see here is that the y components cancel. So for every dq that we can create on this side of that center line, we can produce a dq on the other side that's going to have a symmetric contribution to the electric field. And so the y components of all of these will cancel. And so the only thing left is going to be the x components. And so let's look only at the x component, knowing that that will be giving us the electric field overall. So if we want to know the x component here, we need to know the angle. So how do we get the angle? Well, let's take a look. We can apply our SOHCAHTOA. So our cos theta is going to be equal to r divided by the square root of y squared plus r squared. Okay. And I'm just going to wall this off a little bit. Keep things nice and organized. So now that we have an equation for our angle, we can get an equation for our DEX. And so that's going to just be, if we look at this, right, we're going to have this theta in here as well. That's the same angle. Okay. And so that means that we can add a cos theta term in order to get us to the x component of the electric field. Okay. So now what can we do? Well, let's rewrite our DEX equation. And what we're going to do first is consider how to eliminate our dq term. We've got our Coulomb's constant. Now, what's our dq term going to be? Well, what is dq? Our dq is going to be our lambda times some dy. So really, let's just shift our angle equation up a little bit. And we're going to write this out. So our dq term is really going to be equal to lambda times some dy. And our lambda, we know, is q over L, so dy. Okay, so now we can put our dq in terms of q, L, and some increment of y along that total L value. Okay, so our dq is going to be q over L dy. And that's all over y squared plus r squared. Now the other thing we can substitute is cos theta. Now writing it this way made sense because this was all equal to just the electric field times cos theta was our x component of the electric field. But now let's put it in terms of the variables we already have in this equation. So we're going to say, well, let's rewrite it as r is over our square root of y squared plus r squared. Okay. Now, it might be easier to keep track of this if we just write it as 1/2. Okay. And that way we can combine it with the other side of the y squared plus r squared. All right. So now that we've introduced something that's hopefully going to allow some terms to combine. Let's rewrite again. And now we're going to have k and then let's keep the q over l together because those are just numbers. That might be useful. And now we've got an r term and a dy term. I'm going to keep the dy term at the end. And underneath in the denominator, we're going to have y squared plus r squared to the 3 over 2. All right. Now this is a nice equation that describes the dx, the dE in the x component for our dq, but what we really want to know is what is the electric field for the whole L, for the whole length along this extended object. And the way we're going to find that is by integrating both sides. Okay, so what we're going to do is we're going to add up this contribution from dq along the entire length of L. We're going to start with some dq here, and we're going to work down, work down, work down, work down. And we're going to integrate all of the contributions to find out the electric field at that point. Okay, so that means that we're going to have on the left side, we're going to integrate and get the electric field in x, and then we can pull out k q over L, because those are just a number. They don't vary. And here's where it gets interesting. The rod is symmetric around that center line. Okay. So if that's our point of reference, that center point, what we have is an integration from plus L over 2 to minus L over 2, because there's 1/2 L on either side of the center. So we're going to integrate from L over 2 positive to negative L over 2. And we're integrating all the things that are going to be relevant. So we've taken out the constants. Okay. And so now we do our integration of this term. And so we have E in the x direction is equal to, got our k q over L. And then we integrate all of this, and we end up with y over r, y squared plus r squared to the 1/2. And we're going to evaluate that at L over 2 and minus L over 2. And so this gives us an E is equal to k q over L. So now we're going to substitute those values in. So we've got an L over 2, and then got an R L over 2 squared plus R squared, square brackets, 1/2. All right, and that's minus. This will be minus L over 2. It'll be R minus L over 2 squared plus r squared to the 1/2. All right, and so when you simplify all that, we end up with an equation for EX that's equal to KQ over R times, let's make this a little nicer, 1 over R squared plus L over 2 squared square root. Now this is actually going to be the electric field, because we, as we discussed before, due to symmetry of the problem, the y components of all these dq's will cancel. And so we're left with just the x component. Now that's true only for the line here right in the middle. So if we go off center from that point, the symmetry is no longer the case, and all that cancellation is no longer going to happen. All right. So let me just see if I can slide this up, because we're not quite done yet. It would be nice to keep this on one page. Maybe it'll work. Maybe I'll just squeeze it there and we'll kind of cheat just a little bit. Okay, so now what? We've got an equation here for the electric field of this rod along that center line. But, you know, it still probably could be a little bit better. So let's work with it a little bit more. Okay. So we've got this electric field of the rod, and it is KQ over R. And we've got a 1 over R squared plus L over 2 squared. That's all square rooted. Okay, so what else can we do here to make things a little bit nicer to manage? Well, let's pull out the L over 2, okay? Because I would prefer to be able to bring the L out in front, because then if we can bring the L out in front, Q over L is our linear charge density, or lambda, and so that would make things a little nicer. So let's do that. So we're going to have K Q over R and 1 over. Now I'm going to draw this a little bigger, so we're going to do a little bit of work. Well, let's draw out that L over 2 term. So we're going to draw out this L over 2 squared from the rest of it, which means that we end up having a 4 R squared over L squared term there. It's a little nicer. Okay. And then plus 1, because that's where it originally was. So we pulled that out. Okay, so because that's squared, that's fairly straightforward to pull out of the square root. So we've got K Q over R, and now what we can do is just pull out that L over 2 term. We've got an L over 2, and then we've got the square root sign containing all the rest, where it was 4 R squared over L squared plus 1. All right, maybe we can tighten that up a little bit. Okay, so What else can we do here? Well, let's do what we plan to do all along. What we're going to do is we've got our k. Now we've got, well, we can bring the 2 up. So it'll be 2k q over our L times the rest of this, which is 1 over square root. I'm going to bring the 1 out front, so it'll be 1 plus 4r squared over L squared. Alright, so now we're able to convert that q over L to our lambda term. So it's 2k lambda over r times 1 over square root of 1 plus 4r squared over L squared. And there we go. So there we have what I think is a better equation for the electric field of that rod along that center line. Now it's all in terms of some constants out front, and the linear charge density is there explicitly, which is nice. Are we done? No, we got one more thing I want you to consider. So consider an infinite line of charge. And that is, i.e. L goes to infinity. Let's just bring this down to the next page. Okay, so we have this equation already. Okay, so given all this, what's going to happen as L goes to infinity? Well, if this term is infinity, then that means this term, is going to go to 0. So this is 0. And if that's 0, then square root of 1 is 1 over 1, so this whole thing becomes 1. So that means what we're left with is a much simpler expression, which is, I'll draw this a little thicker. So that is the electric field of this rod, we'll say infinite rod, so infinite line of charge is going to be equal to 2k lambda over r. And that's much, much simpler. And what we see from that equation is that it really just depends on the charge density and the distance away. And interestingly, it's not the distance away squared. It's just the distance away. And that's because you've got this contribution from all these distant points along that infinite line of charge that are always coming into view and playing a role in the overall electric field at that point. So that's where we're going to stop. We have gone through quite a bit of work to show how you get the electric field of a charged rod at a point along the midline that's bisecting that rod. And really you do that thinking about the little dq and its contribution to the electric field, or dE, and then doing an integration across the entire object. And this is a very useful and powerful approach, really demonstrating why calculus makes problems solvable. So we then get an equation, which was great, but we thought it would be better to put it in terms of our charge density, since that's a defining characteristic of the object. So then we got an even better equation. And then you see the significance of it yet again, kind of formulating it in this way, because when we consider what happens when this goes from a defined length to an infinite length, then you're really just left with that term here. Okay, so that's all for now.